Hi, recording is rolling. So it is Monday, January 30th. So I'm gonna have a couple of your questions. I'm gonna throw you guys, and then we're gonna go into this Kahoot on. I've got some conceptual questions related to light, color, optics. Give those to you guys. Hand this paper out. So this paper is just for you guys. Okay, these are the Kahoot questions you guys are about to see. Okay. And actually, I want to start with the mirror questions because a couple of the last questions that you guys can see. We can go over those before they pop up here. Okay. Then we'll have a few minutes. I've got some demos lined up for you guys. We're going to open up the forensic science textbook, show you guys an application of that. Got a couple of videos. Okay. Okay, I wrote a quiz for you guys over the weekend, so I'll get that to you guys soon. I think I'll just make this a take-home quiz. You guys know these take-home quizzes. I like to draw a lot of questions from these conceptual questions. So as long as you guys are following along with Kahoot, again, you don't have to turn this in, but good thing to have the right answers. Can help you out on the quiz. Okay, so mirror puzzles. Okay, so one of the questions you're going to see here is the question. How much of a mirror do you need if you have it positioned at just the right location to be able to see your entire self? Like, for example, I know this mirror, like if it's a flat mirror, I can't see my entire self. I can put this on the wall and like stand back from it, and I'm going to see probably part of myself. Okay. Suppose you're like 6 feet tall. Like, how much mirror do you need to see your entire self? So, take you guys through this answer here. They've got like a dresser mirror. You guys see this could be like a flat, plain like dresser mirror. Okay. And I'm gonna have a stick figure. Right? I could draw this guy like anywhere, like arbitrarily, or any arbitrary distance. Right? You can put him close to the mirror, like far away. Let's say I put him like right over here. That'll make him like the same height as the mirror. Like if he's the same height as the mirror, then he should for sure be able to see his entire self. Right? Isn't that be true? Right? But it turns out he doesn't actually need the entire mirror to see his entire reflection. Okay. Here, let's do a multiple choice. Wait, this is one of these questions, isn't it? All right. It's number 18. Is it a quarter of his height? Is it half of his height? Does the dresser mirror need to be his full height? Or does the dresser mirror need to be twice his height? Right, so that's your multiple choice options. This is number 18, looking at number 18. Okay, so we're answering number 18 before we actually go into the Kahoot version of this. Okay. Let's see, show hands what you guys are thinking. So this guy looking at this mirror, okay, how much of the mirror does he actually need? Right, quarter, half, whole, or double the size, right, to see his entire reflection? Show hands. How many guys think that he only needs a quarter of the mirror to see his entire height? Who says he needs half the mirror to see his entire height? Right. Ooh, that's a lot of votes there. Who says he actually needs the full mirror, like as I've drawn it? Right. And who says he actually needs double the mirror? Okay, so a bunch of guys chose option B. Okay. I think you guys are right. Okay. So let's check out why. You guys remember last week we did a bunch of ray diagrams with reflections, and Paul Hewitt showed one that involved like a candle, and that's similar to what we're doing because it's a plane mirror. Okay. Do you guys think that he should ultimately see himself the same height, opposite side, right? Like equidistant, same height, right? Trying to draw his reflection here. So, something kind of like that about. Okay. Trying to draw him like equidistant. I don't know if I got it exactly, but I'm trying to get pretty close, right? Okay, so, right. That's what you should see, right? If you did like a whole ray diagram, yada. But I mean, you guys know this without ever taking this class, right? You see yourself in a flat mirror all the time. Okay. Now let's add to this a little bit. We give him an eyeball so he can be an observer. Right. So he's looking at this reflection. Right? And let's say he's looking at the top of his head, he's looking at the bottom of his feet. Right. So right. Okay, so here's him looking at is it here should draw object, image, kind of deal. Right? Okay. So he's looking at the top of his head. So it looks like the top of my head is like bam, that point in the mirror. It looks like there's a ray of light coming from back here. Okay. Whereas you guys know actually that ray of light will boing bounce off the mirror. Right. Kind of like that. Law of reflection, right? And he also looks down and he sees the bottom of his feet. He says, hey, looks like my feet are like coming from like down there. It looks like there was a ray of light came from this direction. Okay. But that ray of light actually boing bounced off the mirror from back here. Okay. That's why, right? Is it? Okay. Ah, and here it is. Here it is. Okay. You guys see that the section mirror he actually needs is this bit right here. Okay. You guys see that? Okay. So you can cut off the few inches up here, and you can cut off this whole bit down here, and now you can see his entire reflection right there. And this should be half of this. Let's get an exact measurement. Okay, so I just sketched this up. Let's see. Exact. I'll verify that. So in my picture, the sky is let's call that 6.8 centimeters tall. So this guy's height is 6.8 centimeters. Right. Let's see what the height of this patch of mirror is to see its entire self. So it looks like 3.4, I'll call it. So the height of the mirror is 3.4 centimeters. Ah, there you go. That's 3.4 compared to 6.8. That is half. Yeah, so this is the right answer. Okay. Now notice that's independent of how close or far away from the mirrored surface he is. He could back up like 3 times farther away, and he still needs that exact same patch of mirror. Of course, the catch is he needs that exact location, right? If it's too low or too high, it won't suit, so it's got to be right there. Okay? If you're ever next to a large mirrored surface that's flat, try this out yourself. I know one place I saw this myself was I was at an airport at night, and all the walls were like glass, so and it's dark outside, so you could see your reflection. Right? If you stand kind of next to the wall, right, you look at your reflection and say, hey, where's the top of my head in that reflection? Where's the bottom of my feet in that reflection? Right, you like make marks on the wall, maybe mental marks. Okay, so there and there. You start backing away from that mirrored surface, you'll notice that your reflection exactly aligns with those exact same 2 spots on the surface, right? It doesn't actually change, it doesn't get pushed, no, doesn't shrink like that, doesn't shrink like that. It's the exactly same place. Okay, gotcha. Okay, and there's a, okay, actually there's sort of a follow-up question to this, but maybe I'll save that for the Kahoot. Okay, you guys got that? You guys ready for this Kahoot? All right, so, all right. Switch over and knock out the rest of these conceptual questions. All right, so switch to screen 2. All right, Evan's on. I'm gonna pause this recording and wait for the rest of you guys to hop on here. All right, recording's resumed. And all right, here we go. Light, color, optics, all that stuff. Right. Compared to the speed of radio waves to the speed of light, okay, so you guys remember radio waves, light waves are all electromagnetic waves. You guys remember that? Here, let me find, here it is. So radio waves, microwaves, infrared, visible part of the spectrum, your eyes can see. Ultraviolet, X-rays, and gamma rays, they're all the same phenomenon. They all travel at 3.0 times 10 to the 8 meters per second. Now, they have different wavelengths and different frequencies, but they're all the same speed, right? Am I true? Especially through a vacuum, right? Which is fundamentally different from the others. All right. Yeah, sound waves, right? Because the other 3 are all electromagnetic waves that travel at the speed of light in their electromagnetic spectrum. Okay? Like gamma rays are high frequency, short wavelength, right? And radio waves are like long wavelength, low frequency, right? Light waves are right in the middle. Right? But these 3, like the red, the blue, and the yellow, can all travel through a vacuum, right, at the speed of light. But sound waves, entirely different. The sound wave is a longitudinal wave, right? The other 3 are transverse. Sound wave is longitudinal. That's a pressure wave. It needs a medium to go through. Travels much slower, like a million times slower than the other, right? So totally different, completely, like fundamentally different. Okay. All right, Evan and Mia, getting the points. The difference between a radio wave and a light wave. Yeah, it's wavelength. Remember, to travel at the same speed, especially through a vacuum, right, which is 3.0 times 10 to the 8 meters per second, right? They're all electromagnetic waves too, right? It's wavelength because a radio wave has a longer wavelength than light wave, right? Like radio wave is usually like a meter and longer. Anything that's like a meter long and longer. Light waves is like hundreds of nanometers, right? You guys see that? It's like what 380 to 750 nanometers. We're talking about for visible part of the spectrum, right? Really short wavelength. Okay? Another answer choice that would have been valid would have been frequency, right? Different frequencies. It's just not an option here. So wavelength or frequency. Compared to speed in air, the speed of light in water. Yeah, it is slower, right? So you guys remember refractive index? You guys remember I broke out that glass block was shining the laser through it. Right? This was the whole explanation for refraction. Like, why does light refract? Why does it bend? Right. Well, okay. Well, some do like it slows down, and then you go through this whole process. Like, okay, well, it's got to bend for it because it slows down. And the index of refraction of water was like 1.33. So light goes about 33% slower in water compared to air. You kind of think of it that way, sort of. All right, Evan on fire, got Cole, Mia, Jack, getting points. Glass is transparent to visible light, but not to what? Got a trivia question. Okay, yeah, I hadn't told you guys that, so I wouldn't expect you to know it. But this is pretty cool trivia, though. Right? So different parts of the spectrum can travel through different materials. Right? Like, how about these walls? Like these walls are opaque. We can't see to the classrooms next to us because they block visible light. But if you had a radio with you, do you think you could tune in like radio stations? Do you guys think radio waves are going through the walls and through the ceiling? Yeah. So radio waves can travel through the walls, but not visible light. But hey, what about like that glass window right there where you can see out the hallway? So visible light gets through that glass, but apparently not infrared and UV. So this is kind of interesting, right? There's like a quantum mechanics explanation for this. We'll talk about the tail end of the year. It has to do with like like a electron configuration thing. What was I gonna say this? Oh yeah, so let's say you're like on a long road trip, right? So you're inside a car, right? You can clearly see through the windshield, like visible light can get through, so you can see where you're driving. Right? But you probably don't worry about like putting on sunscreen going on a long road trip as long as you're inside the car. Now, if you're like outside, like walking around, outside in the bright sun all day, then okay, you definitely got to wear sunscreen. But as long as you're inside the car, you might not really think too much about that because that windshield should block the UV, right? Clouds. Ooh, all right. So say you and your friends want to go hang out at the beach for a couple of hours. Should you wear sunscreen? Yeah. But then one of your friends says, well, hold on. It's actually a really cloudy day. I mean, we should still go to the beach, but it's kind of cool weather. It's really cloudy, overcast. Should you still wear sunscreen? Yes, because those clouds are not going to block the UV. The UV goes straight through the clouds. You could still get a sunburn. Yeah. The world looks different in UV compared to visible light. I've got a Veritasium video, show you guys near the end of class. Looks at the world through UV. It's a little bit different. Electron vibrates up and down 1,000 times per second. That will generate a wave with what property? 1,000 times per second. What is that called? 1,000 what? Yeah, that's a frequency of 1,000 hertz. That's what 1,000 times per second is. Okay. In case you forgot that, remind you guys. Suppose you hear like, so that could be a frequency of 1 hertz because that's 1 beat per second. But what if you heard something like, that would be something closer to like 4 beats per second, which would be like 4 hertz, right? And then if you heard like 1,000 beats per second, 1,000 hertz, okay, that's what we're talking about here, right? So 1,000 times per second, that's hertz. How far is a light second? All right, so a light second is a distance, just like a light year is a distance. I know second a year might be, well, hold on, it's not like a time, but we're saying like how far, like a distance, does light travel in that time, right? Because light has a speed, right? So you guys know that the speed of light is 3 times 10 to the 8 meters per second. So that means in 1 second, it will travel 3 times 10 to the 8 meters, right? Well, okay, how do you go from meters to kilometers? Well, that's 3 decimal places. So that's 3 times 10 to the 5 kilometers, which is that right there. Okay. So in 1 second, light will travel 300,000 kilometers. Right? By the way, the distance from the Earth to the Moon is pretty close to that. There's like a 1.3 second delay. So like back in the 60s, 70s, astronauts bouncing around the moon, talking back to NASA officials based on Earth. Right? There was a 1.3 second delay between one small step for man and then when Earth received the signal. Right? Did you guys see in the graphic is gone? Or maybe what is the delay from the sun to Earth? How long does it take sunshine to reach the Earth? Yeah,
8 seconds.
like eight minutes. Yeah, like 8 minutes, right? Yeah. Okay, so right, like 8 minutes. Yeah. So pretty good distance. Long. I think it's something like 400 times farther away than the moon is. The sun is. Right? Yeah, there you go. So we're talking about light years, light seconds. We're talking about distances, right? The distance that light travels in those times, those intervals of time. The distance light travels in a year is called a light year. Yeah, that's true, right? So now we're talking about distances like across the galaxy or to other galaxies, right? Usually, that's like 50 light years away, right? If you travel at the speed of light, right? Take 50 years for that light to reach, like that. Let me Google this real fast. I should know this. All right. Width of Milky Way light years. Let's see what this is. Oh, that's more than I thought. Okay. Well, my Google search is saying 100,000 light years. Is that really the width of the Milky Way? That seems crazy. Oh, okay. I guess so. Colors on a TV screen or your phone screen. What is that? Okay, so color addition. You guys remember the difference between color addition and color subtraction, right? So color addition is like light bulbs turning on, and there's really only 3 bulbs on your phone. You guys remember what they are? Red,
green, blue.
There you go, red, green, and blue. It's sometimes called the RGB standard, right? From that you can make all the colors that you can see with your eyes. And if you have them all flashing, then what color does that make? White. Right. So if you have like a white background, that means all the bulbs are turned on, right? So that's color addition. Right? Versus if you have inks or paints, right? You mix all those together, doesn't it like subtract more and more light out and take things like really dark, muddy color? Right? That would be color subtraction. But yeah, for your phone, color addition. The more lights turned on, more it is closer to like white light. Color addition. Color seen on a printed photograph. There you go. There's your color subtraction. So your ink printer. Do you guys remember the colors in your ink printer? What are they? Yeah.
Cyan, magenta, yellow.
Boom. That's it. Yeah, cyan, magenta, and yellow. There you go. Right. And if you mix those 3, guys, what if your printer spits out cyan and magenta and yellow all on top of each other? What does that make? That means black. Yeah, there you go. Right. It would look pretty much indistinguishable from black ink because it absorbs all the color. That's subtraction. It's subtracting all the wavelengths one at a time. When blue and yellow paints are mixed, the resulting is green because why? Yeah, there you go. Between blue and yellow, all colors are absorbed except for green. So yeah, like look at my photo here. Like yellow paint will actually reflect both like red and green light, but your eye just interprets it as like yellow. Right? And then every color paint you add to that, it will subtract those wavelengths one at a time. So you add some blue, and then the only thing reflected back is the green because it like subtracts it out. You know, everything besides the green. All right. I got Evan on fire on the top. Got Cole, Jack, Mia, and Capri. Top 5. 3 primary colors for additive color mixing. Yeah, red, green, blue. Right. So your colors on your phone screen. Additive mixing. Red, green, blue. Did I show you guys a close up of RGB pixels? I think I showed you guys an image last week, but in case you, okay. Say this again. Where's images? There we go. So that's what your phone screen looks like up real close. It looks like that, right? RGB. Ooh, cold, top spot. Difficult to tell a roadway from a car on a rainy night because oh, okay. Yeah, this one thing we had. Okay. When the road usually looks diffuse, when it's dry, it becomes a mirrorly wet. Let me switch over here and point out a page in the book that shows this. Okay. So different kinds of surfaces reflect light differently. Zoom in here. Okay. You see paper versus mirror. Okay. So paper is like a diffuse surface. So here you come like a bunch of rays of light, and then once it hits the surface, it'll scatter in all different directions. So your eyeball could be at all different angles, and it would look like the same thing. Same thing if I take this laser light, okay, and I shine it here. Okay, it doesn't matter the angle I shine the laser or what angle you're at. Like everybody can see the laser light on the paper, which is diffuse, and it looks the same. Okay? But if this was a mirrored surface, okay, get the flat mirror, right? Do the same thing, shine the laser light. Okay, oh, okay, like I see the laser light there. Then move my hand, so go from a diffuse to a reflective surface. Now we don't see the laser light anymore, okay? Because it's reflecting only in one direction. It's doing like this thing, boing. Okay? Now you can only see it from that point of view. So when you're driving around on a road, okay, if the road is dry, it looks like the one on the left. It's diffuse. When the road is wet, it looks like a mirror. So that's harder to drive on, harder to navigate. Go here. All right, refraction. Okay. So you guys remember light will travel at different speeds through different media. Like through a vacuum, it's 3.0 times 10 to the 8 meters per second. Through air, it's like almost that. Okay. But then through water, it's that divided by 1.33. Right? Right. So you start from that, the fact that light slows down through water, through glass, through diamond was another example we're looking at. Okay. Okay. And then you go through this whole process, like, okay, well, here's why light has to bend because it slows down. Right? You guys remember that whole thing? Okay. It's like a whole process we talked about last week. You need to go catch the video and talking about Snell's law. Like, where does that come from? All right, Evan, to the top spot. When you see a wet spot mirage on the road, you're most likely seeing an image of, where's that come from? What's the deal there? It looks like water, but it's not actually water. Oh, all right. Hope you guys got that. Yeah, sky. Here, I want to draw this one on paper too. Flip over here. So And so you're driving along in your car, right? You're looking ahead and, oh, whoops, zoom out a little bit here. Yep. Right, and it looks like there's like this puddle in the road. Like, hey, is the road like wet? You guys seen this, right? Right. No, usually you see this on like really bright days, right? It has to be really bright outside, right? But then you drive up to it and it's like this puddle disappears, right? And you can never reach it, right? It's like a rainbow. You can never reach and touch it, right? So what's going on? Well, it has to do with that the road gets really hot, like the surface is really hot. And when the surface is really hot, well, there's this temperature difference. Like, you know, you can go around and touch the dirt and the plants and the sky and say, okay, I can touch all those things, but I sure don't want to touch this really hot asphalt, right? And the layer of air right above it is super hot. So here comes in some, there's like a cloud or some sky over here, right? Right. And yeah, we have a ray of light coming in like this, right? But then it gets close to the surface, right? And then it refracts. It's going to refract this way. Right, and it'll bend straight up into your eyes right here. So you're driving this car, right? And you see what looks like a puddle to you. Say, hey, looks like it's like a puddle light came from like back here. But really it's refracted light came from the sky in front of you. Right? And that happens when the road is really hot and the layer of air above the road is really hot as a result. Causes that refraction. Okay. All right, cold back to the top. A person standing waist deep in a swimming pool appears to have short legs because of yeah, there you go, refraction. So you guys see this poster, there's the pencil in the water, and it appears to be all good out of shape, appears to be short, refraction. Here we go, the shortest plane mirror that you can see your entire image. There you go, half your height, right? Now, of course, the catch is you have to have it positioned, you know, just in the right place. But yeah, if you're 6 feet tall, you have a 3-foot mirror, there is a place you can put it on the wall. You can see your entire self. And then if you get closer or back further away, same story. Ooh, I think I just gave away this next question. When you look at yourself in a pocket mirror, then hold the mirror further away. What do you see? Okay, so this kind of goes hand in hand with the dresser mirror question. Remember, it doesn't matter how close or far away you are. Or I was talking about like being at the airport, looking at the glass wall at night, right? So yeah, okay, here's a mark on the wall at the top of my head, mark on the wall at the bottom of my feet. If I back away further and further, top of my head, bottom of my feet still seem to be the exact same places on that mirrored surface. Okay, so same thing with a pocket mirror. You can try this yourself. Here, yeah, so if you get hold of like this flat mirror, right? You see like, how much of my face do I see? And then I hold it further away, or closer. Doesn't matter. You still see the exact same amount of your face. You can try that. Okay. Reason that lines look wavy at the bottom of the swimming pool when viewed from above. Why wavy? Yeah, refraction, right? Light refracts at different angles because of the uneven surface. Now, if the surface was completely smooth, then you wouldn't see it all jaggedy like that. But if it has any kind of, okay, so you gotta get that. Uneven surface, refraction, different angles, it's all jaggedy. All refracting lenses rely on light having a what? Yeah, there you go. Has to have a slower speed inside the lens. Right? The fact that light slows down allows for refraction. Right? If light didn't slow down, then you wouldn't get that refraction. See if there's like a consistent speed everywhere, there would be no refraction, so you couldn't like magnify with a refracting lens, right? A magnifying glass wouldn't work, right? If it was same speed, no refraction. Okay. Yeah. right, and last question. Oh, so Evan on 5 to the top. I gotta race for first. A magnifying glass underwater will magnify how compared to the one in air. So that glass has an index of refraction. Air has an index of refraction of like 1.0. Water has an index of refraction of like 1.3. Yeah. All right. So you guys all got that right. Yeah. So let's say the index of refraction of glass is like 1.5, similar to what was in Snell's law lab from last week. Right. So if you compare 1.5 to water 1.33, then yeah, light will slow down a little bit going from the water to glass back to the water. So there's a little bit of refraction, but not very much. Okay. Versus if you hold that magnifying glass in the air, going from 1.0 to 1.5 back to 1.0, right? There would be a lot more refraction, a lot more magnification. Yeah. So take that magnifying glass underwater, and it might work a little bit, but not very well. But take it back to the air, ooh, it'll magnify a lot more. That's actually related to the forensic science example I'm about to show you guys. Let's go to the podium. With the bronze, we got Jack. With the silver, Cole. And the gold, Evan. All right. Yeah, nice job, guys. So hold on to that paper because next few days I'll get you guys a take-home quiz, and some of those questions probably gonna pop up. All right. So next thing I want to show you guys here. Let's do so I'm breaking up the forensic science book. Okay, and I'm gonna go to glass evidence. So let's say you go to a crime scene, there's like shattered glass. You're trying to figure out who committed this crime, maybe what vehicle we're driving, where did shattered glass come from? Can we make a match somewhere? Now, I gave you guys some indices of refraction last week. I told you guys for air or vacuum, like vacuum, it's 1.0 exactly. Air, it's like extremely close to that. For water, it's like 1.33 index of refraction is. For like diamond, I think it was the other one I gave you guys, like 2.42. But I didn't tell you what it was for glass because there are different kinds of glass. Like this glass, I think was like 1.5. Broke this out, it smells a lot with it. But if you know, maybe some glass is like 1.48, and others it's like 1.51 or like 1.56. Okay? And then you could use that to make a match. Say, this glass came from like this sample, maybe like this windshield of this car, right? And then you can track down that. But how do you, I mean, if you have a nice painted glass, like if you have a really nice shape, like this is very convenient, like semicircle, you could do the same lab that we did last week. Shine the laser through, watch it refract, and then figure it out from there. Okay. But in a crime scene, you're probably just going to get like a little tiny fragment. So it's really small, it's all jaggedy, not a very convenient shape. So how do you figure out that index of refraction? Well, it's related to that idea of like the magnifying glass not working well under the water. In fact, if the glass had an index of refraction of 1.333, just like water does, the magnifying glass wouldn't work at all, and it would look completely transparent underneath the water. Now, yeah, not only would it not magnify, it would look completely invisible. It wouldn't be able to do this at all. Look invisible, right? So you can take advantage of that. So what they'll do is they'll compare known refractive indexes of different liquids to an unknown refractive index piece of glass. Okay? So they'll drop this glass and there's some kind of like liquid or oil that they use where they can change the temperature. This one method I've seen, right? They can change the temperature of this particular liquid. I forget what liquid they use to mention it here, right? And that will change the refractive index of that particular liquid, right? So maybe it has a range of like 1.4 to 1.6 or something, right? Okay. And then at the moment that the glass goes invisible, like this last one, see it's like completely invisible. Well, it looks invisible because there's no refraction, so the light just goes a straight shot through it, right? And that means that the index of refraction of the glass matches the index of refraction of the liquid. You say, oh, well, it's 1.53 exactly, right? And then they can match it to whatever sample it came from. Okay. You guys get that? How that works? All right. All right. So last thing I got for you guys. Yeah, got a couple of video demos. What color is a mirror? And what does the world look like in UV? Just got a few minutes, so whatever time we got, switch over here and play that out rest of the class. I'm gonna go ahead and stop the recording though, but if you're at home, you can find this on YouTube, and there they are.